Okay, welcome to lecture number 3 in week 4 of Machine Learning Foundations. In this lecture, we will start the discussion about similarity and diagonalization of a matrix. In particular, we will define what it means to say a matrix A is diagonalizable, and we will relate this to the the idea of linear independence of eigenvectors of this matrix. So the question of whether a matrix is diagonalizable is strongly related to how many linearly independent eigenvectors I can get. Can I get enough to diagonalize this matrix? And then we will look at a very special case. Imagine you have an n cross n matrix. If I can get n linearly, if all the eigenvalues of this matrix are distinct, then it is diagonalizable because I can get enough eigenvectors, and that's a particular special case, interesting special case that we will see. And in the subsequent lectures, we'll build up this theory to go to the final claim, which is to understand which is the spectral theorem, which says that any real symmetric matrix is diagonalizable. We'll get there in steps. That's the final claim that we are heading towards. So, welcome everyone to yet another lecture on linear algebra, the module that we are looking at. In the previous lecture, we looked at eigenvalues and eigenvectors and looked at some motivation using ordinary differential equations. And today we will look at a very important topic associated with eigenvalues and eigenvectors, which is similarity and diagonalization of matrices. So, what is a diagonalizable matrix? So, let us start with the definition. A matrix A is diagonalizable if there exists, this is a symbol for exists, there exists an invertible matrix S such that if I do S inverse AS, then what I get is a diagonal matrix. So, if this condition is satisfied, which is like saying that if I can find an invertible matrix such that S inverse AS equals lambda, capital lambda, which is a diagonal matrix, then the matrix A is diagonalizable. Now, let us dig further into this. When is a matrix diagonalizable? A matrix is matrix being diagonalizable is really tied to having enough independent eigenvectors. So, let us understand this. So, what do I mean by this statement? Let us so I will make this claim precise. So, suppose A is a n cross n matrix with n linearly independent eigenvectors. Say x1 until xn. This is the set of eigenvectors. Then A is diagonalizable. Why? I mean, for diagonalizability, what do we need to show? We need to manufacture a matrix S which should be invertible, and S inverse AS equals S inverse AS is a diagonal matrix. So, how do we do that? Let me show you such a matrix. Let S equals, you take all this eigenvectors that you have and put them as columns in the matrix, and let me call that matrix S. So, the question now is S invertible? So, I would say pause the video, think about this. Now, what is the rank of S? Rank of S is n because x1 to xn is a linearly independent set. Yes, because it's a linearly independent set. So, it has full column rank and it is an n-cross-n matrix we are looking at. We are looking at vectors in n-dimensional Euclidean space. What is AS? AS is A x1 until xn, which is nothing but A x1 till A xn. But these are not any x, these are special vectors, these are the eigenvectors of the matrix A. So, let me write n and say n independent eigen with corresponding eigenvalues lambda 1 until lambda n. So, lambda 1 is the eigenvalue with corresponding eigenvector x1 and so on. So, what we got is lambda 1 x1 until lambda n xn, right. Is that clear? Now, I could write this as x1 until xn and take this product with a diagonal matrix, which is just the eigenvalues. And that is the same as S multiplying a diagonal matrix, where this is a diagonal matrix with entries all the eigenvalues. So, AS is S post multiplied by a diagonal matrix, and that is enough to claim diagonalizability, which is equivalent to saying S inverse AS equals a diagonal matrix. We already showed that S is invertible. So, the point is a matrix is diagonalizable if it has enough independent eigenvectors. We will show a simple case, special case, call this a claim. If lambda 1 comma lambda 2 are the eigenvalues with corresponding eigenvectors x1 comma x2, and lambda 1 and lambda 2 are distinct. So, lambda 1 is not equal to lambda 2, then x1 comma x2 is a linearly independent set. So, eigenvectors belonging to different eigenvalues, corresponding to different eigenvalues, are linearly independent. That is really the claim. We can show this. So, we will start with the linearly independence requirement. The condition is like suppose some constant times x1 plus constant times x2 equals 0. Let me call this equation 1. Now, if I operate A on both sides, then I get 0, A of 0 is 0, but this is nothing but C1 times A x1 is lambda 1 x1, A x2 is lambda 2 x2. So, call this equation 2. which is like saying that C1 into lambda 1 minus lambda 2 into x1 equals 0. How did I get this? This I obtained by taking 2 minus, okay, so that is what I did. Now, lambda 1 is not equal to lambda 2 and x 1 is not equal to 0. So, what does that imply? So, in this equation which is above, let us say this one. In this equation, lambda 1 minus lambda 2 is not 0, x 1 is not 0. So, the only way that equation can be 0 is when C 1 is 0. Similarly, C 2, it can be argued that C 2 is also 0. It just implies x 1 comma x 2 is a linearly independent set. Now, extension of this claim, which I am not going to prove, but it is going to follow the same arguments, which is if lambda 1 to lambda n are distinct, then their eigenvectors x 1 to x n are linearly independent. I would leave this as homework. Proof homework. Yeah, but use the arguments that I have done above and you can argue this. Okay. So, we will do an example. Take this matrix A and do 1, 4, 2, 3. So, let us calculate the eigenvalues and eigenvectors of this matrix for some practice. So, A minus lambda I is nothing but 1 minus lambda 4, 3 minus lambda. So, the characteristic equation is, so I recommend you pause the video and do this on your own and then verify with what I got here. The roots of this equation. So, roots are, let us say lambda 1 equals 5 and lambda 2 equals minus 1. So, now is the question, is A diagonalizable? The answer is yes, because it has two distinct eigenvalues. It has two distinct eigenvalues. So, the corresponding eigenvectors form a linearly independent set and you got enough independent eigenvectors to diagonalize the matrix. So, what is pending now? You need to find the eigenvectors. Yeah, finding eigenvectors. So, let us take the first one, lambda equals 5. So, the corresponding matrix is, you have A minus lambda 1 I turns out to be 1 minus lambda is minus 4. You have the other two entries same, and 3 minus 5 is minus 2. Now, what is the null space of this matrix? Null space of A minus lambda 1 I. If you look at it, if I just add the columns, that's enough. So, this belongs, and that's the only thing that belongs. Yeah. So x1 is 1 1. Now then let's look at the second eigenvalue, lambda 2 equals minus 1. In this case, A minus lambda 2 I turns out to be 2 4 2 4. Now, so how do I make sum of column 0? I can take minus 2 times the first column and 1 times the second column. So, minus 2 1. This is one possibility. I mean 2 comma minus 1 will also work. Belongs to the null space of A minus lambda 2 I. So, x2 equals minus 2 comma 1. And that's about it. Now, you can form the matrix. All you have to do is the matrix S is going to be stack the eigenvectors minus 2 comma 1, and the diagonal matrix is going to be the eigenvalues, which is 5 comma minus 1. Just be careful, when you add these eigenvectors, you have to add the eigenvalues also in the correct order, and then you can check. This is something that you can easily check. S inverse A S equals lambda. This is something you can check, which is 1 1 minus 2 1 inverse A is 1 4 2 3 minus 2 1 equals 5 0 0 minus 1. Okay. So, that is an example. Now, please try to solve some more problems on your own, diagonalized matrices, take even slightly higher dimensions, say 3 cross 3, and solve these problems. I will continue with a few remarks or observations about this. Remark number 1. S inverse A S equals this, or A is S lambda S inverse, one and the same. The question now is S unique for a given matrix E? Think about this. The answer is no. Why? If x1 is an eigenvector, then so is any constant multiple of x1. So, if you take the previous example, instead of taking 1 1, I could have taken 2 2, and I would still get a valid S. Yeah. So, the columns of S can be scaled to produce, to get S prime such that S prime inverse A S prime is also a diagonal matrix. The diagonal matrix will not change. It's the the diagonal entries are all eigenvalues, that won't change, but the matrix containing eigenvectors will change. Now that is something that we will make precise in the second remark. Suppose A can be written like this, and suppose column 1 of S is Y. Now, what is column 1 of S lambda? Column 1 of S lambda is nothing but lambda 1 into Y, that is just by definition. Now, what is column 1 of AS? This is nothing but A pre-multiplying the first column AY. Now, we know AS equals S lambda, which is the same as saying AY equals lambda 1 Y, implies lambda 1 is an eigenvalue and Y is an eigenvector of A. So, the point we are trying to make is if A is diagonalizable, then the diagonal matrix can only contain the eigenvalues of A, and the matrix S contains the eigenvectors of A. But matrix S is not unique, but there are only one set of eigenvalues for a given matrix. So, the diagonal matrix is going to be the same. Yeah. Let us look at another remark, which is can look at powers of A. So, suppose lambda is an eigenvalue and x is an eigenvector of A. Then what can we say about A square x? A square x is nothing but A of A x, but x is an eigenvector. So, it is A of lambda x, which is same as lambda times A x, which is again equal to lambda square x. Now, if you suppose S inverse A s is a diagonal matrix, then the question now is S inverse A S square, sorry, S inverse A square is that equal to lambda square? Now, think about this. Given whatever I have written above, think about this, which is like saying that can I use the same matrix of eigenvectors and diagonalize A square? The answer is simply yes. Yes. Why? It is easy to see this. So, if you take S inverse A s into S inverse A s, what do you get? This is the same as this into this, which is like saying that S inverse A square s equals. Now, there is nothing special about the square. Yeah. Argument, the argument above works for a general positive integer keygun. That is, you can infer S inverse a power k S is just this. Now the last remark. If you want an example, take this matrix. You can check K does not have two linearly independent eigenvectors. You can check this easily. All you have to do is calculate the eigenvalues, which are very easy to calculate, and calculate the corresponding eigenvector, and you will get only one eigenvector. Yeah, you only get one eigenvector. Okay, a recap of this lecture before we end. So, what did we learn in this lecture? What we understood was that we understood the concept of diagonalization of a matrix. And for diagonalization of a matrix, so what happens is there are two matrices that come into play. The first matrix is where all the eigenvectors go in, and it is going to be invertible. And the other is a diagonal matrix which contains the eigenvalues along the diagonal for a particular matrix. So if I get enough, a matrix is diagonalizable, say n cross n matrix, we saw that n cross n matrix is diagonalizable if I can get n linearly independent eigenvectors, otherwise it's not. Then we looked at two simple examples where, for example, 2 cross 2 matrix where we could get two linearly independent eigenvectors, and we could directly calculate the diagonalized form. We could write down the decomposition of this matrix to show that it is diagonalizable. And subsequently in the next lecture and the following lectures, we will try to understand which matrices are diagonalizable and which are not. In fact, the main theorem that we are heading towards is Spectral Theorem, which shows that any real symmetric matrix is diagonalizable.